we are going to tell about plane geometry, and one of the main actors of today's lecture is a so-called measure. I'm going to tell about a simple example of measure about area, and from the more general point of view, I am going to tell about metric properties of plane. This property includes lengths and areas. This lecture, one of the last two lectures devoted school repetition course, school repetition material. I recall that we have a segment maybe with two endpoints A and B, and point D divides this segment on two parts. We have a simple corollaries, one corollary from triangle axiom, which asserts that length of segment AB is equal sum of lengths segment AD plus segment DB. And second assertion, second axiom, if we have two segments AB and A prime, B prime, and one of them we can apply onto other, the lengths of two segments are equal. In the case of plane, we have more complex picture. Intuitively, we can imagine two such figures. One of them has such form and consists from three squares, and other has other form, but also consists from three squares, and we have divided first of one onto three squares and collects these squares in new way, and we obtain the new figures, and we can mean that the areas of these two figures are equals, and this is a natural way to define area in the plane case. We are going to define this notion by axiomatic way, and this definition based on the following two properties. First of them, I am going to define some number characteristic of the plane figures, and these figures, for example, some polygons and maybe not convex polygon. After I extend this definition on the arbitrary plane figures in a more complex way. And for polygons, my definition based on the following axioms. First of all, two equal polygons have the same area regardless of the position they occupy in the space. This properties is an analog of properties for lengths of segments. In other words, if we have two equal figures in the various in the various positions, and I can move first of them such that after this motion I can apply first of these figures apply on 2, and these figures coincides. Then these figures have the same area. Area is invariant under some kind of motion. Two axioms. Polygon P, which is the sum of adjacent polygons A and B has the area equal to the sum areas of the areas of polygons A and B. We will denote the area by the as the M of P, and these properties you can rewrite as if P is sum A and B, the point denotes that these polygons can only adjacent on adjacent side on adjacent side, and in this case we have following equality. From these properties, easy to follow that we have some polygon, and this polygon we can divide onto some of polygons which has such properties. Other words, each of them has only one adjacent side, and we collect these parts on the new way. Maybe such. Maybe such way. The new polygon has the same areas as one, the first polygon. But we can, after them, we must choose some polygons, some figure which has the area which equal some unit of areas. As a rule, such polygons is a square which has the side of unit length, and we define the area of such polygons as a unit, the measure of such square is equal 1. And using such polygon, we can define the measure of other figures. First of them, the rectangle. If this rectangle we divide onto some squares, and let this square has A columns and B rows, and the measure of such rectangle is equal product of lengths of his sides A and B. In the case when A and B are integer. In the case when these two rational numbers, we can divide it onto more parts, and using common procedure we obtain this proposition in the case of rational numbers. When this number are real, we must to use more complex procedure, so-called the notion of limit, and now I will not to define this procedure exactly. we can formulate the first theorem, which is corollary of this definition, namely theorem 1. The ratio of the areas of two rectangles is the same base is equal to the ratio of the lengths of their other sides of their altitudes. We have two rectangles, one of them rectangle ABCD and other KLD, and these rectangles have the common side AD, and length of AB is equal C, the length of AK is equal D. This theorem is direct corollaries of property 2, and the reformulation of this assertion about areas of rectangle is equivalent this assertion. If area of ABCD, if the area of ABCD is equal AC and area of AKLD is equal AD, this ratio is equal AC divided on AD. This ratio is equal, ACAB, I'm sorry, AB. The ratio is equal the ratio of these altitudes CB. And if we have the assertion of this theorem, we can deduce from this assertion this definition of the area of rectangle. And the corollary of this theorem this assertion, measure of rectangle ABCD is equal AD on AB. This product of lengths of base on the length of altitude. ABCD is a rectangle. Using this a simple assertion, we can conclude for this assertion the various formulas for various for areas of simple features. For example, the first corollary. The case of parallelogram. Maybe the theorem. The area of a parallelogram is equal to the product of the lengths of base and altitude. Proof. Let A be length of A and H the length of altitude. And let we have parallelogram ABCD. Let B K the segment which perpendicular to base AD. And we have triangle, right triangle ATB. Move this triangle such this triangle coincide this new triangle D K prime C. This triangle is equal. And using the property 2, we have we have the measure triangle or parallelogram A, B, C, D is equal measure triangle ABK plus measure KBCD and equal measure of rectangle KBCK prime, and this measure is equal A, product A and H, and we obtain the assertion of this theorem. And second corollary of this base theorem, this base theorem 1, maybe this theorem 2, the formula for area of triangle. Theorem 3. The area of triangle is half of product of lengths of its base and altitude. Proof. Let A, B, C given triangle. And let construct some parallelogram A prime, C prime, C, such the triangle B prime is altitude. We have the following equalities of triangles. Triangle A, B prime congruent equal triangle A prime B, and triangle B prime C is equal triangle C prime B, and parallelogram A prime C prime C is union of following four triangles. A, B, B prime, B prime, B, C, which union of these two triangle consists the triangle ABC, and other the sum of other two triangles A prime B plus I'm sorry, it's union A prime B and B C prime C. The measure of this union is equal measure of triangle ABC, and we have measure A B or A prime C prime C is equal the sum of these two measures. Each of them is equal measure of triangle ABC, and we have equalities, and from this equality follows that measure ABC is equal measure A prime C prime C, half of this measure, and is equal A product AH, half of product AH, and we obtain the assertion of this theorem. We also obtain the more complex formulas for other figures. If we have arbitrary polygons, we can divide these polygons on the triangles, such that each of them have only one adjacent side. And from axiom 2 follows that area of such polygon is the sum of areas of these triangles. For example, if we have some n polygons, in this example 6 gone, and let all sides of these polygons are equal, and this all angle is equal, and we want to calculate the area of this triangle. We divide this this polygon. We divide this polygon on such triangles and calculate the areas of each of them. This areas is product 1/2 of the length of side, and maybe length of side is equal A, and R the length of altitude of these polygons, and we obtain such formulas. Maybe H. Maybe H. Later, we express the altitude from the angle in this triangle and length of side, and obtain some closed formula for area of such polygon. But this method we can apply in the general case for calculation the area of arbitrary polygon divides. We can divide this polygon onto some union of such triangles and calculate the area of each of them. And sum of such areas is the area of arbitrary polygon. This method can be applied in the more general situation, for example, to calculate the area of the circle. The idea is following. We inscribe into circle some convex polygon with equal sides, and describe also such polygon. And we have, if we will consider the polygon with more sides, the length of each side is less than for previous polygons, but the area of new polygons is larger than the area of previous. And we have increasing sequence of areas of such polygons. But from other side, we have other sequences of areas of described polygons. And in this way, when we consider the polygons with more sides, the areas of such polygons became less and less, and we have two sequences. One of them is increased and other sequences is decreased. And these two sequences has the common limit, and this limit is the area of such object. It's more general way for calculation, but this general way works for arbitrary figures. But I will not consider in detail this common way. The same for other following lectures, maybe later, and maybe in the other course, in course of analysis, calculus. Okay. Now I am going to consider the way calculation of areas of triangle using some so-called trigonometrical function, sine and cosine. And using these new formulas, we obtain simple formulas for areas, various figures. I call the following definition. Let we have some right triangle with hypotenuse C and two legs A and B, and let beta the angle which adjacent to A and opposite to side B, and let define two functions of this angle. One of them is called cosine, and other sine. The first of them is a ratio of adjacent side to hypotenuse, and other is the ratio opposite side to hypotenuse. Easy to check that sum of squares of this expression is equal unit. Using the definition, we obtain the sum the ratio A square C square plus ratio B square C square. And using Pythagorean theorem, we obtain the ratio C square to C square. This formula is very useful. From this definition, we either conclude the following theorem. This theorem expresses the side in arbitrary triangles from the lengths of two other sides and angle between these sides. And let we have arbitrary triangle maybe and let the length of side AB is equal small a, length of AC is small b, and length of AB is small c, and let angle BCA is equal gamma. Theorem. C square is equal A square plus B square minus the product AB cosine gamma multiply on 2. It is very useful, useful formula. Let h the altitude in the triangle A prime is perpendicular to side AB, and length of A prime is equal h. And easy to check. This fact follows from Pythagorean theorem that the length of AB, more precisely, square of AB is equal sum of squares A prime B plus A prime. But and length of AB is equal C, and we have that C square is equal sum of squares AB, sum of squares lengths of segments AB and A prime. But A prime B, I'm sorry, A prime sorry. A prime, I'm sorry, A prime B and C A prime. Sorry, A prime B. B prime. Okay. Yeah, that's right. A prime, the length of A prime is equal B product B and sine gamma. And A prime B is equal A minus B cosine gamma. Because the length of C A prime is equal B product B and cosine gamma, and this is difference between A and A minus B cosine gamma. And using these formulas, we can substitute this expression for two previous expressions. And after simple calculation, we obtain the following equality. C square is equal B sine gamma square plus A minus B cosine gamma square. And after the simple calculation, we obtain B square sine gamma square plus A square plus B square multiply cosine square gamma minus and using this identity, we easy to obtain the proving assertion. A square plus B square minus 2 multiply product AB and cosine gamma. The first of the one of the two theorem. The second simple theorem, the theorem about some property of other trigonometrical functions, sine. And the second theorem is called sine theorem. Theorem 4 maybe. Theorem 5. We have triangle ABC and small a, small b, and small c are the lengths of the corresponding sides. And the theorem asserts the that the ratio A and let alpha, gamma, and beta the measures of the corresponding angles. Alpha the measure of angle A, beta the measure of angle B, and gamma the measure of angle C. And we have that the following ratios are equal. Ratio A to sine alpha is equal B to sine beta and C to sine gamma, and is equal to R. R is radius of circumscribed circle. To prove this theorem, we need some simple assertion. I call some simple assertion. First of them, if we have circle and we have inscribed angle and also we have central angle, inscribed angle ABC and central AOC, and both of these angles has the same arcs. I assert that the measure of angle B is half of measure of central corresponding central angle. Easy to check that some angle AOC plus angle AOB is equal the measure of a straight angle. And from other side, the sum of two equal angles BAO and ABO plus angle BOA also is equal measure of straight angle by the theorem of sum of angles in triangles. And the first assertion let the measure of central angle is alpha and measure of inscribed angle is beta, and we have the following equalities: alpha plus sum AOB is equal measure of straight angle, and 2 beta plus AOB is also is equal of measure of straight angle. And from this we obtain that beta is equal the ratio the half of alpha. If we have more general situation, for example, such, we easy to check the general position for this partial case when one of the sides of angle intersects the central point of circle. Using this theory, this lemma, we can to prove the other lemma too, namely let maybe lemma 2, and we have some inscribed triangle in the circle, maybe triangle ABC. The same triangle, this. But I will consider only one angle alpha and one side A. Let the O the center of this circle. Let C prime is the diameter of the circle. Let's consider the triangle C prime BC. I assert that this is a right triangle, and angle is a right triangle. The angle C prime BC is right because the arcs, the corresponding to this angle arcs, is half of this circle. And let's note that the angle C prime and A, more precisely, the angle C prime B and angle C A B has the same arc. And from lemma 1, we can conclude that this angle are the same, and this angle is equal alpha. Using the definition of sinus, we obtain that A is equal C prime C, which is the diameter, and is equal to R on sin alpha. And from this we conclude that ratio A small a to sin alpha is equal to R. From if we apply this lemma to all other sides of this triangle, we can conclude that the ratio A sin alpha is equal to R. The ratio B sine beta is equal to R, and the ratio C sine gamma is also equal to R, and conclude this assertion. Okay. Now we can apply this theorem to some simple assertion, and let's solve some simple problem. And I need also I need also in the other theorem 6, Thales theorem, very simple theorem, and I suggest to prove this theorem as exercise using property of triangle equality. Theorem 6. Theorem 6. We have two line which has point of intersection O. First line L1, L2, and on the one of the side we can choose some points A1, A2 and A3, the arbitrary 3 points, and let parallel lines which in each of these parallel lines intersect other lines L2 in the points B1, B2 and B3. And the theorem of Thales asserts that this ratio are equal. A1, A2 to B1, B2 is equal A1, A3, the ratio A1, A3 to B1, B3 is equal to the ratio A2, A3, B2, B3. I mean that the lengths of these segments, the ratio of lengths of these segments are equals. Easy to see that these 3 triangles are similar. We have the same angles, and using the properties of triangles, we easy to conclude the assertion of this theorem. That's all. And after this theorem, I would like to consider solution of some problem. This problem we can also consider as the simple theorem, but I think that's more right to try to solve this, to prove this problem as some exercise. Problem 1. Calculate the area of triangle if its three sides is given length of sides. Let we have a triangle ABC, and let the length of sides of triangles is given, namely the length of AB is equal C, length of AC is equal B, and length of BC is equal A. This data is unique, defined the triangle, and define the area of this triangle. We must to calculate exactly the area of this triangle. In other words, we want to express this area from this given data, namely using A, B, and C. First of all, note that the area of triangle is equal half of product of length of one of each side onto altitude. The altitude is perpendicular to the sides. For example, let's consider altitude h A prime, and let length of this altitude is equal HA. And we have this equality, the product, the half of product A, HA. And let the angle C is equal gamma. And HA, by definition of sine, is equal product B on sine gamma. And we obtain that area of this triangle is equal A, B, and sine gamma. easy to see that need to express the sine gamma using the length of sides of triangle. And this is our claim. And this claim we can to use the cosine theorem. This theorem express function cosine using the length of sides triangles. Namely, we have the following qualities: c square is equal sum a square b square minus product ab on 2 and cosine gamma. And from this equality we easy to check that cosine gamma is equal a square plus b square minus c square divides onto twice product AB. And using the equality square cosine gamma and square sine gamma is equal 1, we deduce that cosine gamma I'm sorry, sine gamma is equal and let's and we obtain the following formula. Let's transform and simplify this formula. After easy simplification, we obtain this simple expression. I'm sorry. After let's using this formula and obtain the formula for the area. I write this formula in the following form. And substitute this formula in this expression. And easy to check this. We obtain this expression. And let's simplify this expression, namely and the last simplification and let's introduce a new notation. Let small p is half perimeter. This expression is small p. This expression is p minus 1. Oh, sorry. 2 p minus 1. Oh, yes. Yes, 2p minus 1, this expression. I'm sorry, this expression 2p, this expression 2p minus 1, this expression 2p small minus b, and this expression 2 p minus a. 1, 2, 3, 4, and after them we obtain this expression, this following expression. Following expression p this following closed simple formula. And the answer is following. We obtain the exact formula which expressed the area of triangles using the length of each sides, namely maybe a questions about this formula. For some training, maybe better to understand this simple calculation, I suggest to solve the following problem. Oh, I'm sorry. Oh, my time is out. I'm sorry. Maybe question. I sent some problem by mail, and I will wait for answer. I'm sorry, bye-bye. У меня какой-то заскок. Я почему-то решил, что в 10:40